So let's start with the rate equation. It doesn't really matter what the rate equation is for today, but since the exercise has got that one, I'm using that one. So if I did the experiment at different temperatures, if I did it at 20 degrees and then 30 and 40 and 50 and 60, something similar to what we did with the disappearing cross last term, did it at a whole bunch of different temperatures. And I make sure that I keep my concentrations the same. So that's one of my control variables. The concentration of A and the concentrations of B remain the same. As I heat the reaction up, obviously it goes faster, yeah? The rate is going to increase with temperature. We've all known that since year 10. Rate increases with temperature because more particles
with energy equal to greater than the activation.
Yeah, do you remember that little phrase we used? More particles have energy that's greater than or equal to the activation energy. Remember that? Okay, so as we heat reaction up, it goes faster. A and B, or concentrations of A and B are staying the same. Rate's going up. So K must be going up. We can't have the maths work with the rate going up and nothing else changing. If rate's going up, K must be going up. So K increases with temperature. Which sounds like a really good occasion to ask you to draw another graph. You've only drawn about 10 so far in this topic. How does rate change with temperature? Just draw a line. Worst that's going to happen, it'll be wrong. So it does depend a little bit on what numbers are on our temperature axis here, but let's assume, we're doing the reaction at, I don't know, 25, 35, 45, 65, sort of ordinary lab temperatures. So the origin here would be, I don't know, maybe 0 degrees centigrade. Anyway, most people have got it going up, that's great, but I'm not seeing the shape I want to see. Okay. All right. So we've got a lot of straight lines. It's not a straight line. Didn't you do this last term? There's one on the board, isn't there? Been on the wall all this time.
Presume that the activation energy was already met, so the temperature was already where most particles were greater than the equal to the activation energy.
What?
So say if a reaction occurs at 20 degrees, and we presume that we start at 20 degrees and then we increase.
Yes, but 20 degrees is not an activation energy. Activation energy is 50 kilojoules per mole or something. And at 20 degrees, some particles will have that activation energy and most won't. Remember your Maxwell Boltzmann. Right. Okay, so it's a slightly different shape from the graphs that we saw last time. What shape is it?
Exponential.
It is an exponential. Well done.
Passes through 0, 1, sir.
What was that?
Passes through 0, 1.
Passes through 0, 1. What do you mean?
This is math.
0, 1, like coordinates.
In maths, an exponential graph. When anything is
All exponential graphs.
most of the exponential.
I don't think that's true, but anyway,
This mark is wrong then.
let's move on. So an exponential.
If A equals 1.
I don't want to get into the maths of it because it's complicated and you don't need to know much about it, and also I don't know much about it. But there is a button on your calculator with e to the x written on it, and in or around that it should have ln of x, where ln stands for natural log. Natural log meaning it's to the base e, where e is a super number that mathematicians love, a bit like pi. It's 2.718281828. I don't know. It repeats a little bit, but then it doesn't. It's a transcendental number. It never repeats, just like pi. So it's a special number. Is anyone mathsy enough to know why it's special?
Because if you differentiate that, then you get something again.
That's right. The y by dx of a graph, the differentiation or the gradient of the graph at any point is y equals e to the x. In other words, it's got its own gradient at any point, which makes it a bit special. I'm not sure why that's so exciting to mathematicians, but I'm sure they have a heap of fun with it. And we just really need to know which button on the calculator it is, and we need to do a little bit of work. Has anybody not worked with logs at all? Never seen a log before, apart from the big ones floating in the stream. I'm talking about.
As in, like log to the base. I don't know.
Log to the base 10.
Usually we use log to the base 10. So a log is a measure of what?
Kind of like power, so log to base 10 is how many powers of the
Okay.
10.
Call it the index usually. Yeah. So if log of 1,000, well, we can express 1,000 as 10 to the 3. So log of 1,000 would be 3. It's a measure of the index that the 10 is raised to. Logs used to be very useful ways of solving difficult problems. We have log tables. I was given log tables when I did my A-levels in maths, and like most people, I used a pocket calculator. But they were around for a long time. They were very useful before people had pocket calculators. So log is assumed to be base 10. ln, natural log, is to the base e. You don't need to worry about what that means. Really, you just need to know there are different buttons on your calculator and you have to press different buttons. And if you can find that button on your calculator, and it's usually the shift function will be, the other one. So if one button is e to the something, the other one will be log of something. As long as you can find that button and use it correctly, you know enough about logs and natural logs to do the chemistry. Okay, so it's time to introduce the relationship between K and temperature, and it looks like this. EA, top. That's right, isn't it? I always get tangled halfway through writing that formula. I've also lost my, oh no, I gave you my book too.
You know the R and the T, is that like for
It is,
minus
yes.
8.31?
Exactly the same.
Yeah.
Yes.
Oh, very nice.
That is right, isn't it? The good news for you is that you are given that formula. It's the Arrhenius Rate Equation.
I met
Swedish then.
Who was Swedish? Yes, thank you. He was the Svante Arrhenius was the chemist who did a lot of work on rate, and as it says in the booklet, in 1899 he predicted that adding carbon dioxide to the atmosphere would warm the planet up, which in 1899 I think is what you call a heads up, really, considering how little action we've taken on that information for the last 124 years. Anyway, so that's the Arrhenius Rate Equation. That is given to you in the exam. You don't need to learn it. Let's just go through the different things. So the Arrhenius constant. If you're going to get an equation, you've got to have a constant named after you. It doesn't have any units. It's the best way of thinking about the Arrhenius constant. It's a bit like the collision frequency. It gives you an idea of how often atoms are banging into each other. EA, of course, is the activation energy. Just note, it's in the equation. Remember the whole SI units thing? We have to go into SI units whenever we're using, like proper maths, grown-up maths. So joules per mole, please. Of course, all delta H values and delta G's are. You done delta G yet? They're all kilojoules per mole, but you'll get to it soon. Okay, R, we know R. What's R? 8.3. What is it? It's the gas constant. Yeah, that's right. Ideal gas constant. 8.31 joules per Kelvin per mole. And T is obviously temperature. It's got to be in there somewhere. Measured in Kelvin. Okay. Yeah, so that gives you the exponential relationship between temperature and our little k, the rate constant. Right, let's just do a little exercise based on that then. I'll just grab some numbers. So we'll give you that in joules per mole. So activation energy is going to be 50,000 joules per mole. We know R is 8.31. And what I'm going to do is compare the value of K at so 293 and 303 Kelvin. Assume A remains the same, so we can ignore A. It's a constant, so let's assume it remains constant. Dear. So what I want to know is what's the value of e to the minus EA over RT at 293 and 303 Kelvin, and then we'll divide one by the other and see how much the rate of reaction has changed by increasing the temperature by 10 degrees. Okay, this is really an exercise in you using your calculator properly, putting those numbers into your calculator and sticking an E in front of it, e to the power of that. I'll leave you for a moment. Okay, so we just so really this is just about you learning how to use the E button, but hopefully you got 1.21 times 10 to the minus 9 and 2.38 times 10 to the minus 9. Yeah. If you put the big number over the small number to turn it into a fraction, it's almost 1.97. If we were working to 2 decimal places, or rather, if we were working to 2 sig figs, it would have been 2. So, in other words, for a 10-degree increase in temperature, pretty much doubles rate. 10-degree increase, it's just a good rule of thumb. 10-degree increase doubles rate. And it explains that shape of that curve. If you think about how we've gone, if the temperature's whatever it is there, and then we get a 10-degree increase there, so my rate must have doubled, and then another 10-degree increase there, so it must have doubled again, and then another 10-degree increase there must have doubled again, and that's why you get that characteristic shape getting steeper and steeper and steeper, which we all remember from COVID, right? If the number of cases doubled every 6 weeks, whatever it was, then after 6 weeks you've got 1,000 cases, and the next 6 weeks you've got 2,000, and then 6 weeks later it's 4,000, and so on, and it exponentially rises.
Like rabbits.
Hey?
Rabbits.
Like rabbits.
Yeah.
Do they get COVID as well?
No, so far.
Okay, let's check. Don't worry.
Rabbits breathe, rabbits breathing.
Okay.
I'm sure they do.
Let's just do a little bit more maths, because I know you love it, but fortunately, again, you don't need to know this. this is going to be given to you as well. But I'll just explain where it comes from. So if we could just gear up our maths, people who like that kind of thing. I'm going to take logs both sides. So I'm going to get log k equals log a e to the minus ea over rt. Well, log k is just log k. I can't simplify that at all. But if I've got two things multiplying each other and I want to kind of separate them, what's the rule there? Okay, so that would be log a plus log ea minus ea over rt. Now the other important log rule here is if I have log of e to the something, then it's equal to the something, exactly right. If I had log of 10 to the 3, I had it up here, didn't I? Log of 10 to the 3 equals 3. If I have log of e to the minus ea over rt, it's just minus ea over rt. Okay. Just going to rearrange that a little bit. Log k equals minus ea over r. I'm just putting that term at the front there, and then 1 over t is going to go there, and then plus log a there, which might seem like I've just made things more complicated. But what I've done here is I've made a y equals mx plus c graph. Yeah, okay. So that form of the equation, by the way, that one there will be given to you. They won't necessarily make it obvious that minus ea over r is going to be, you know, your gradient, but that's how it is. If I've got a straight line graph of log k against 1 over t, then the gradient m will be minus ea over r, and the y-intercept will be log a. Okay. So this is something that you need to be able to do. So we're going to do it, or at least we're going to start doing it now. So much lovely maths. If you could turn to exercise 2 in your topic booklets. You'll see there's some reminders of the definitions and the meanings of the symbols for the Arrhenius Rate Equation there. But towards the bottom of the page is a table of data. There's four points. You've been given 4 experimental data sets. So you've got a temperature and a value of K, which is presumably being worked out by doing some experimental work, the sort of which we've seen already, how we can calculate K from experimental data. So your first job is to work out 1 over T and log K for each of those temperatures and K values. When you've done that, we're going to plot a graph. But just work out the data first, and then I'll explain a bit about the graph in a moment. Never mind. Okay, so here's our graph. So the 1 over t axis will be at the top, the log k axis will be going down. Your graph will then look something like that. And you want to stretch the 4 points. Oh no, we're out of time. You want to stretch those 4 points across as much paper as possible. So when we find the gradient, it's as precise as possible. Can I leave you to finish that graph for homework? You've got some paper. and then we'll Thursday. Just the graph. You don't need to do anything else. Just get the points plotted and draw a best fit line, and the best fit line pretty much goes through or very close to every point.
My pen left inside.